Hello, everyone. My name is Archie. I'm a PhD student at the University of Central Florida here in Orlando. Today, I want to walk you through a series of research work in our lab titled Physics-Informed Deep Learning Applications in Transportation. My co-author on this work is my advisor, Dr. Sharia Arguel, and I intend to make these a two-part videos. In the first part, I'm going to walk you through the theoretical background of this research work. And the second part, we are going to see the case studies and going to present the results and some discussion the implications of that PIDL applications. So let's jump into it. So these presentation's content mainly come from these three publications. We have two more papers to come. Here is the overview of this presentation. So I have 6 major components. So as I said, in this part 1 video, I'm going to cover the first 3 from introduction, physics of the traffic flow, to PIDL for traffic state estimation. And the second part, we are going to see the case studies and results. So when we talk about the task of traffic state estimation, I think the challenge mainly lays in the limitations of the traffic observations that we have, the traffic state data that we can obtain, and that's mainly due to these 3 factors of installation cost, storage limit, and no detection method is 100% accurate. Sometimes we view the inherently the data will contains inaccuracy in the measurements. So in this work, we want to present the PIDL applications in this transportation domain. So here in this figure, you're actually going to see 3 major categories of this traffic state estimation approach. In the column on the left, you will see this model-driven approach where you have a traffic flow model, and through calibrations, you're going to obtain these estimations of traffic state, either that may be traffic flow or traffic density or speed. In the middle, this column where you will see is actually is the data-driven approach, where you have you're going to utilize or you rely on historically observed traffic data, and you apply some statistical or machine learning methods to get this TSE for the purpose of TSE. But some limitations on that is this usually will requires a larger amount of data available, which is not necessarily always the case. And on the right, so finally, we will have this physics-informed deep learning approach, which kind of combines parts from these 2 established approach. So I'm going to take a traffic flow model. I'm going to use that as the physical knowledge or the governing physical equations in this case. And then I'm going to I will train the model on some observations, some observed traffic data, and the learning architecture will come from a deep learning neural network. And that's kind of like the 3 major components in the PIDL approach for TSE. So now for next, let's see some basics concepts regarding traffic states. What are the physics that we are talking about in this transportation domain? So first, in this equation 1, we are actually going to see the relationship between traffic flow, which is here Qxt, and density rho xt, and the cumulative count nxt. So what is cumulative count? So that means given a predetermined location x, and given a selected time stamp t, how many vehicles have already passed this location at this time. And we will see actually the relationship that's shown in equation 1 is these partial derivatives equations here. That we will see Q is actually the partial derivatives of n with respect to t, and rho is a partial derivatives of n with respect to x with the location, and they take the negative value. So here actually we will quickly see in the next slide is by twisting or some minor adjustments of this equation, we can make it a conservation law, which is coming up here in the next slide, where we can introduce the LWR conservation law in this traffic flow theory. And it's very simple. It's just when the cumulative count n is differentiable in both the time and space domain, and we can have these two parts adding them together and make it this conservation law, and it should equal to 0. And this is a partial differential equation, and will play a major role in the physics-informed deep learning as the governing physical equation of traffic flow. So after these, let's briefly touch on another concept in the traffic flow theory, which is fundamental diagram. I'm sure many of you are very familiar with this concept. Is the diagrams that depict the relationship between traffic states. So what figure 2 actually here gives you the Green-Shields fundamental diagram. And I think as soon as you see this linear relationship, which is depicted on the lower left, or the subfigure between speed and density, and you see like as the density increasing, your speed is gradually decreasing. We know, actually that's the Green-Shields fundamental diagram. It's very simple, it's very straightforward, and here I'll give you the formulations of Green-Shields fundamental diagram. Again, it's a linear relationship, and as stated on this slide, VF is the free flow speed or the maximum speed that we can obtain on this diagram, and rho m is the maximum density, maximum value of vehicle density on this road. So after we talked about fundamental diagram, the last part of the physics that I want to introduce here is this cell transmission model, which is also very straightforward, as we can think about a row segment as a finite cells, putting them together, and vehicles on this road traveling are just can by particles flowing from the preceding cell to the succeeding cell. The notation here is actually n is the number of vehicles present in the cell, and y depicts the flow from the previous cell to the next cell. And here we have equation 4, which is also a way to describe this which is also a conservation law, which, as you see, the left part of this equation was left to the equal sign is the changes or the evolution of the number of vehicles in that same cell I with respect to time. And the right is actually give you the differences between your downstream flow and your upstream flow. So so equation 4 depicts this relationship, kind of like the differences between flow in and flow out will result in the changes in this cell regarding the number of vehicles. So and on the next slide here, I'm actually, this is just a two-dimensional visualization of the traffic state. So on the previous slide, we see this segmentation or discretization of a road segment, spatially, like with respect to location X. And here we are just adding another dimension. So not only we have X, now we have T. So now we see these temporal bins and spatial bins, and the colors here just indicates the number of vehicles. So so the redder the color, actually, that shows the more number of vehicles, and then you have the green color where we have like very or a less amount of vehicles. But that's just a color scheme. It give you an idea of like, oh, actually, this is the evolution of traffic states on a road segment. It's not necessary. It doesn't just have the spatial domain. They also have this temporal domain as well. So that's actually all the physics of the traffic flow theory that I want to review for now. I think that's enough like background to jump into PIDL and to see what makes a physics-informed deep learning a unique deep learning architecture. And let's move on to the next slide. So here, I want to talk about the differences between a PIDL and a regular deep learning neural network. And what PIDL has is the ability to encode the governing physical equation as a priori knowledge into the training process of this deep learning neural network. And what that means is actually we're going to see on the next slide, the architecture has two major components. One part is just a regular deep learning neural network where we tune the parameters, we tune the bias and weights parameters throughout this training process. But another part is actually we are able to compute the physics cost according to the physical equations here, or in our application, the LWR conservation law, as a way to use that cost term serve as a regularization agent to better our estimation output. So here it goes. So when we look at this architecture of a PIDL neural network, we see on the left side, it is just a very straightforward, fully connected, forward-feeding deep learning neural network. So on this figure, it actually shows some, we take some inputs, in this case, X, Y, Z, T, and we produce the output and estimation, which is U. But the differences, or what makes PIDL unique, is actually it has this right part where in this illustration, we actually use some partial derivative terms to construct this physical law or governing equation to compute the physics cost. So how do we actually encode this equation in the training process? By producing two cost terms. So one part comes from this regular deep learning neural network from the left, by basically just comparing my estimation output with the ground truth. And the second cost term is called the physics cost terms, and that basically compare how or measure the disobedience between my estimation output and the knowledge and the priori knowledge and the physical equation. How like if it doesn't comply with LWR, how erroneous that result is. So my final PIDL cost function is actually the summation of weighted DL cost and weighted physics cost, these two cost terms, and that's how I can include the governing physical equation into my training process, and way guide this deep learning neural network into finding the best fitting parameters to reconstruct or to estimate the traffic states. So here in equation 5 is actually a formulation or example of how we can construct the DL cost and physics cost. So if you use mean square error as the error matrices, so here again, we see JDL, or the DL cost, is just the differences between the estimation output here, in this case, the rho hat xt, or the estimated density, comparing to the ground truth, which is rho xt without hat. And the physics cost here, I actually plugged in the LWR conservation law here, and that's how I can compute the physics cost. And that is the gist of PIDL, by including the physics cost into incorporating the physics cost into the final cost function. That's how I can consider the governing equation, and using that serving as a regularization agent to obtain better estimation results. So the last slide for the part 1 video here, I just want to touch on the data sampling strategies of PIDL TSC. It actually kind of like showcase the unique advantage of PIDL, and also kind of like what the application would look like for PIDL in terms of traffic state estimation. So here in the subfigure A, we actually have a Lux-Federiks computation scheme, which can also reconstruct a field of data, but it needs all the boundary and initial observations. So that's kind of like the three borders of this image, which is marked by those black marks. All those boundary and initial data are needed for these mathematical schemes to reconstruct the data. And it also needs the physical equations as well. But when we look at part B, or subfigure B, for the PIDL, now you have a more relaxed requirement on these. You don't need to have all the boundaries and initial observations, and that's also fine to reconstruct or to estimate the traffic states. And that's its major advantage in the sense that inevitably, in TSC applications, sometimes I may have data loss. Sometimes the sensors are not working due to those device malfunctions. I won't be able to have all the data all the time, and that's okay for PIDL approach as well. In the subfigure C and D here, we actually showcase two different data collection strategies for traffic states. So in data C, in subfigure C, you will see these Eulerian observations where you probably have like video cameras or loop detectors embedded at those specific locations. So that's where we see those horizontal black marks. That's kind of like the locations, or like where the traffic state data are available. You do see like there are some gaps in those lines, and that's also just represent the maybe sometimes the data loss, inconsistent data transmission in that case. And in the subfigure D, this Lagrangian observation setting, so that implicates the data sampling scenario where we probably have this data transmitted from connected vehicles. So now we do see those marks are scattered everywhere, so they can come from many locations not predetermined, and they can sample from at all timestamps as well. So that actually concludes the first part of this video. Thanks for joining me, and I look forward to seeing you in the second part. Stay tuned, and I'll see you soon.